Okay, so let's talk about this course. This course is an amalgamation of 3 distinct topics, okay? 3 distinct topics that actually used to be separate courses at one time in the CS department. But they've combined them together, and now you're in 374, and you're in for a very wild ride. So, again, it's consistent effort. But the 3 topics are computational complexity. Computational complexity is a field of research. It's one of the oldest computer science fields of research. And it simply asks, given an infinite time and a machine, is it possible for that machine to solve the problem? Okay, so we're not concerned with solving the problem as fast as possible. That comes later. All we're concerned about, if it's possible for a certain machine to solve this problem. Okay? Why is that the oldest computer science? Because think, before there were Turing machines, all you had were basically like you had gears and mechanical systems, right? Is it possible for a mechanical system like your pocket watch to multiply 2 numbers? Is it possible for the most complex pocket watch in the world, the greatest watchmaker that ever existed, to devise a calculator using just gears and springs and pins? No, it's not. So that's the first question. The very basis of computer science. Is it possible, given an infinite amount of time, for a problem to be solved given a machine? Okay? How complex is this problem? Do we need a Turing machine to solve this problem, or can it be solved using a simpler machine? Field 2 is algorithms or algorithmic design. Most of the problems that you face now in the modern world, you will be able to solve eventually, right? Turing machines or modern computers are miraculous in that regard, in that they have memory, and there are very few problems that you'll face in your normal life that you'll ever question whether or not a computer will be able to solve it. So the algorithmic design problem then, the problem involves to, given a problem that you know how to solve, how fast can we solve it? How fast can we solve it? And why is this different than the first problem? It's because the second problem changes over time. We'll get into that in just 1 minute. Third problem, limits of the computation. Now there are a lot of problems that we don't have efficient algorithms for. It doesn't mean that we'll never have efficient algorithms for it. No one can say that SAT will always need exponential time, and there will never be a polynomial time algorithm for it. No one has proven that. But, you know, I mean, in practice, I mean, you know. So it's probably never going to, polynomial time is probably never going to happen. P probably does not equal MP, at least to the best of our knowledge. And, you know, you sort of, I mean, you can't wait for the theory guys to prove every single thing. You have a life to live, right? So the third problem is asking, given our knowledge about the problems right now, and you're given a new problem. This new problem is unlike anything that's been published before. Where does it fit in terms of runtime, in terms of the context of these other problems? Is it as difficult as SAT? Is it as easy as Dijkstra's algorithm, or basically the shortest path problem? So the third problem is simply the limits of the computation. You're given a problem, and you sort of want to place this problem with its brothers, with the other problems like it in a group, as far as algorithmic runtime. You don't necessarily have to know the algorithmic runtime, but you have to know, if I solve this problem, would I also be able to solve the other problem? That would mean they're both almost the same. Or would I not be able to? Okay? So the question you're probably asking yourself is, in 374, given that algorithms is probably 90% of what you're going to be doing in life, given that most of the FANG companies are just going to be focused on asking you elite code problems, which are all algorithmic design problems, why not just focus on algorithms? Why not? And it's because when we ask that problem, well, it's because you're in school, and so you need to know the theory underpinning the applied work that you're going to eventually do. But basically, when you're in school, when someone asks you how fast can you compute a problem, they are actually asking, can you solve that problem using a deterministic Turing machine, which your computers are? They are asking, if it is solvable, how efficiently can you do it? Assuming you could do it in polynomial time. And they're also asking, if it's not solvable in polynomial time, or if you don't know if a polynomial time algorithm for it, can you use techniques from other problems to make it a little faster? Because even though a problem may not have a worst case polynomial time running time, it could have some little details that you could speed up the solving by a constant factor. That's what's known as heuristics, approximation algorithms, all that sort of good stuff that makes NP complete problems quote unquote solvable on a normal machine, on our modern computers. It's all those things that technically, if we're being technically correct, yeah, it doesn't have the polynomial time runtime, but in practice, it gets solved pretty fast under most inputs. Okay, course structure. Again, I told you guys the CSS schedule, the CSS calendar on my page isn't working, so this is from last semester. I promise I'll get this semester. You'll see something like this on the lecture site. This structure is broken up into 3 parts. The first part is basic automata theory and computability. Sorry, computability. That is the part that asks the first question: can a computer solve a problem X, or can a particular machine solve a problem X? The second part is algorithmic design. That will be recursion, dynamic programming, all the good leak code stuff I'm sure you guys have been grinding on already. And the final part is reductions, undecidability, NP completeness. That's all the stuff that you're going to be, that's the intuition that you need in order to determine if I have a problem X. And I'm pretty sure it doesn't, I don't know if it has a polynomial time solution. Maybe I could relate it to another problem that has been studied heavily and use techniques from the other problem on my problem X. Okay? Okay, goals, algorithmic thinking, basics, tips, and tricks on problems. Understand and appreciate the limits of computation, intractability, and appreciate the importance of algorithms in computer science. Computer science is algorithms. There's no, to me, it's actually quite interesting that this course doesn't come sooner, because everything that you do is like the reason you'll be paid the big bucks in Google or Apple or something isn't because you know C. Any idiot could learn C over a weekend. The reason is that you'll be able to solve things, the critical thinking that you bring to the table that you've been nurturing for these past 4 years. Okay? So algorithms is the very foundation of pretty much everything that you'll do in computer science. It is incredibly important. Okay, so we're going to start off with formal languages and complexity. The blue weeks, the theory, the thing that asks, if you have a problem X, can your machine solve it? Okay? And so before we start off with that question, we have to lay the foundation of our definitions, okay? Because the only way we can communicate to each other as human beings is with very precise definitions, okay? So we need to talk about language theory, okay? Languages. And the first question, why study languages? Or what is a language? So let me give you an example, why and what's. Let's say we have the following problem. Simple problem. You're given 2 n-digit numbers, x and y, and you need to compute their product, right? So, have you seen this problem before? I sure hope so. You should have probably seen it in like 2nd or 3rd grade, right? Multiplying 2 numbers together isn't too hard. The simplest algorithm that exists is the grade school multiplication, partial product algorithm. You have 2 numbers, and you just take each digit, you multiply it, then you account for the order of magnitude for the 2nd digit, and so on, right? So how long does this solution take? it takes, well, it takes n squared, right? Because two n-digit numbers, so you got n when you multiply this number by each digit and the operand, you get that takes n time, and you do this operation n times. So you do a operation that takes time n times. So that's why grade school multiplication takes time n squared. Okay. Now, is there a faster way? Yeah, there's absolutely a faster way. There is a faster way starting in 1960-ish. Karatsuba published a faster multiplication algorithm that ran in n to the 1.58. Then Schranhage and Strassen published a n log n log n algorithm in 1971, and so on, ending with Harvey van der Hoeven that has an algorithm that runs in n log n time in 2019. Not ending. I think there was a more recent one last year. But the point of this is that if we said that this algorithm, that this problem, well, let me come back to that. So the question is, one question is, can we go even lower? Can we achieve an algorithm that runs in time n? Maybe, maybe not. Can we achieve an algorithm that runs in less than time n? Probably not, because we need at least n time to read the inputs, right? So, but that's a trivial bound. So, can we achieve a smaller algorithm? So the question is, if we evaluate problems by how fast an algorithm could solve that problem, how do we compare it to another problem? Let's say another problem. Also, let's say we have the sorting problem that we know quicksort could solve in O of n log n time. Okay, so we have Harvey van der Hoeven that solved n-digit multiplication in n log n time, and we have quicksort that solves sorting in n log n time. Does it mean the two problems are equally hard, equally easy? Hard to say. And if we say anything about that now, the issue becomes what happens in the future when someone published a paper that you could solve multiplication in O of n Ackermann function, n times Ackermann function n times, right? It becomes hard to compare two problems by just runtime of their quote unquote fastest algorithm, because they're two totally different problems. They have different inputs, they have different outputs, and they have different entropy characteristics. That's for you information theory guys out there. So you need a way to compare two problems, right? You need a way to compare problem A with problem B on a very even playing field, in the same sort of structure. How do you do that? Well, let's skip that. How do you do that? You use languages. So what is a language? A language is a set of strings that encodes a particular problem. Okay, so with any problem, you have a string in that for a language that represents any problem, it has a string, and that string represents an instance of that problem. One case of the problem for a particular input and a particular output. Okay, so let's go back to our example, the language of multiplication. How do we encode that as a language? Well, we say the multiplication language is all the strings that represent the possible inputs and the correct output of the function, of the problem. Okay? So multiplying two n-digit numbers together, you could encode that as a string, x times y equal to z. Okay? So you take this problem, that's what multiplication is, and encode each instance, each possible input into that problem as a string, and all those strings form one complete language. Okay? One language that represents that multiplication problem. Now, and so this is one instance of the multiplication problem here. 1 times 1, it gives you 1. 2 times 1 gives you 2. 1 times 2 gives you 2. And you do all possible inputs to the multiplication problem, and you get basically a set of strings, like so. Right? It's an infinite set. It has infinite number of strings. But this set represents what multiplication is. Okay? And you could do the same thing with sorting. You could put in all the possible inputs to the sorting algorithm. Let's for the time being assume that you want to sort 2 numbers only. You could put all the 2 number inputs into the sorting, and the output should be the sorted list. Okay? Now, what does language complexity ask? It asks, now, how do you compare the 2 languages? Well, the key insight for comparing complexity is that if you have a machine that could recognize that this right here, this string, is in the sorting language, but this string, let's 2, 1, what was it, 2, 1, and let's say 2, 1, this is not in the sorting language. If a machine can differentiate between these 2 strings, then the odds are pretty good. In fact, it has to be able to actually solve the sorting language. Okay? So in language complexity, recognition is knowledge. The ability to separate the strings, the valid strings in a problem from the strings not in the problem, that is what determines whether or not a machine can solve this problem. And we use languages because we're able to formulate the problem in terms of strings. We're able to formulate every single problem out there in terms of a set of strings. And so we formulate that set of strings. I have run out of time, so we will get into what strings are next lecture, start off with that. But before you go, I just want to do a reminder, there will be no labs tomorrow, Wednesday. The first homework will be assigned on Monday. The website is under construction. It'll be updated this week. And use Piazza if you have any questions.